Okay, thank you very much, Helen, for that introduction. Yes, I'm a bit worried now. I hear that Jim Austin, you're going to be talking something about Osborne today. So I guess I need to be careful what I'm saying here. Yeah, look, thanks. I guess I should be upfront. I'm probably going to be the low tech talk today. Having a good look at the agenda there. Look, I'm talking about the Osborne deposit. I haven't done a lot of work there, but I'm going to have a bit of a run through, I guess mainly from an exploration perspective with the sorts of data sets that explorationists commonly see. And a lot of this material will be dragged from the Northwest Queensland Mineral Deposit Atlas that we've put together. I think this one was probably back in about mid-2019. So I'm aware time is short, so I'll kick into it. Look, I just wanted to first a bit of an introduction to the deposit, more at spatial type of setting, and what it looks like. So it's essentially a moderate to steeply dipping tabular body with a pretty tough geometry in terms of exploration, which was why it took a little while to be discovered from inception and concept to discovery. And this slide, I just wanted to put up firstly the diagram on the right that shows a couple of the key elements here at Osborne, which are the ironstones. You'll see it in the hashed pattern there, the silica flooding, which is in purple, and then the ore, which is in yellow. And whilst I guess Osborne is typically recognised as an ironstone related deposit and lumped in the IOCG category, it is a little bit different in terms of the timing of the magnetite and the geometrical relationship, I guess, between the magnetite and the ironstones and the mineralisation. And we'll see that as we go through. Now, on the left is just a snap from our geoscience analyst compilation under the Atlas. And why I wanted to show that is the geometry of the ore lenses. You'll see there in the sort of orangey beigey colour, but also there's a drill hole on there that we're going to have a bit of a look through in one of the later slides. So if we continue, sorry, come on. Yeah, so look, first thing I wanted to look at was the minerals that we see, and particularly to do with the alteration here at Osborne. And this is a cross section courtesy of the Chinova guys who gave us a lot of their information when we were putting the atlas together. So this is I guess the standard cross section, and what it shows, you can see here in orange and yellow is the silica flooding, which is the quartz, and you can see that in the yellow, and the ironstone, which is the there in orange, the magnetite. The other things that we have there, so there's the ironstone, and there's a bit of a look at it. So that's essentially the unaltered ironstone. And then if you skip on, this is where it has then been flooded and brecciated with the silica. And then one of the other alteration types that we see is called, they term it the calc-silicate alteration type, and there's a bit of a debate about whether it was well earlier than mineralisation. For example, that's what Adshead is thinking about, or was thinking about in 1995, versus Louis Gautier, who came up with the earlier dates, I guess, probably about 10 or 20 years ago now, and he was more thinking of it as a skarn type assemblage that was closer to the mineralisation age. So there's some of the alteration types that we see in the inner halo, and then the other thing is there's, when you start thinking about some minerals that might be diagnostic for what you see out in the field or in drill core, there's anthophyllite, dolomite, talc, also locally present with the mineralisation, so something to keep an eye out for. So in terms of the outer halo, really it's dominated by albite, and Tulliman's in 2001 documents what he calls a 500-metre wide albite alteration halo. And there's a couple of examples of you can see here. The bottom one is where you have an amphibolite that's been altered with albite and quartz. You can see it's taking on that pale colour on the left side of the stick of core. And the photo above it is what's termed the albitite with the magnetite vein through it. And so in this case, the albite, and presumably it's got some sort of iron oxide dusting through it, it comes across as that orange sort of colour. So that's basically sort of what you're going to see in the outer alteration halo. I should say, the sodium enrichment there, or at least when Adshead was writing one of the main papers on this for the ohm back in 1998, there was some discussion about whether all the albite in this system here was related to sodium from metasomatism or from sodium that came in as a diagenetic or syn sedimentary component. Look, this is one of the data sets that we've been using extensively through Northwest Queensland. This is the high logger data set which GSQ have collected, and I just put this up because I wanted to show what it's telling us in terms of the zonation, but not so much the zonation, but the impact of mineralisation on the host rocks. So that what you see here, this is the drill hole that you can see coming through this ore body. And now the drill hole, this is the thermal infrared, and what we can see is the drill core photos, and then this is the standard high logger display where the colours represent the different minerals. It's not absolute quantitative mineralogy, it's indicative mineralogy. And over on the right here is the shortwave infrared, and then you can see that where the gold and copper grades are here. And I guess the thing to note here is that you know, as we saw earlier on some of the cross sections, silica replacement is so strong here where you have the mineralisation. So that, and we see this in the high logger, the pink colour is the silica. So as you get into the mineralisation, it pretty much wipes out everything else, particularly the plagioclase, which is here in brown, or other feldspars potentially, and it's very much quartz dominated. And in the shortwave infrared, we see the same thing. The grey colour here is the aspectral, where no mineral was able to be detected essentially, and you can see that these greens and yellows, which are the micas, chlorite and muscovite, etc., are totally wiped out as you get into the mineralisation. And interestingly, here when you have a look at the high logger data, you see a little bit of a phlogopite biotite. I don't know if you call it a halo on the outsides of the mineralised zones, but you know, biotite phlogopite alteration has been recognised at Osborne. And I've seen it referred to as essentially occurring in shear zones, and maybe they're in fact nucleated on mafic rocks, on mafic dikes or something, I'm not sure. But it's forming in shear zones, and those shear zones are often what are interpreted as being reactivated and causing you to latent zones for mineralisation. So that's sort of some interesting mineralogy we can see from the high logger. Look, when we talk about halos, it's not only mineralogy, but it's obviously geochemistry. We don't have so much in terms of wide space drilling as you'll see at Ernest Henry, for example, away from the ore body, but we do have the Aircore geochemistry data. And that's shown here. And what you'll see on this diagram, this grey area here is the open pit, and then this is the underground workings, the infrastructure. And I think this was a proposed drive across. This is the Coolthorpe deposit over here, which was later found and only had a little bit, a small amount mined from it. But the interesting thing, and we only have copper and gold, so I've only shown copper here today. This is end of hole values in the copper in the Aircore drilling. For those who aren't familiar with Aircore drilling, it's essentially not a bit, but a blade on the end of your rods that you rotate and you typically extract your sample up through the tubes. And so what happens is it will go into your weathered basement, but not much further. So that your end of hole sample in Aircore drilling is typically sort of your top of basement sample. So the interesting thing to see here is that if you have a look at this copper halo, it essentially, it outlines a pretty significant area, and the green is 50 ppm in the assays. And so you can see that there's a pretty significant area outlined by at least the 50 ppm value of copper, and more so actually over here, over the top of the Coolthorpe deposit. And you're getting up to about 1.5 kilometres away from the Osborne deposit itself here, and you're still ppm level, and you're actually, some of these pink values, you're over 1,000 ppm copper. So it's something to keep in mind if you're drilling through cover in these types of terrains, is that there's often a bit of a dispersion of your elements. Now that's looking at the top of basement. The other, I think, really interesting study that was done out here was initially Louisa Lawrence back in 1996, and then Rutherford did some more work in 2005. And then if you go and dig up the Geochemist's toolkit published by GSQ, Hannon et al. From 2018, that's available on the data portal that GSQ have. It's a fantastic document, and if you go and have a good look in that, there's this study that has been put together, and it's documenting the work by Lawrence and Rutherford. But what it shows is that despite being under 40 to 60 metres of later barren Mesozoic cover, there is a reasonable plume, I guess you'd call it, in terms of these types of elements that get to surface. And you can see in these diagrams that there's a couple of things happening here. This is the top of basement topography where the deposit obviously sits. So it's actually a basement high. And then what you can see, particularly over here in silver, you can see this enrichment up at the top, and that's 0.6 to 1 ppm silver. So you see this enrichment at the top, and that's in the jury crusts that have developed at surface. And you also see a bit of gold in there as well, and I guess to a lesser extent some of the cobalt here. So that's one of the soil anomalies that you find over the Osborne deposit. The other thing is very interesting that this drilling was analysed down through the cover sequence. And it's very interesting what you find in terms of these redox fronts and paleo redox fronts that are developed. And particularly if you look here on the right, there's cobalt, copper to a lesser extent, and zinc as well. There's significant, this is zinc. These red areas off the flanks of the Osborne deposit are 500 to 700 ppm zinc. So these significant anomalies actually within the cover sequence, typically in the ferruginous beds within the cover sequence that can act as a halo to these deposits. So it's incredibly interesting. The last thing I wanted to touch on was the geophysical data, and I know you're going to talk about it, Jim. So this actually might be one of the plots from one of your one of the programs you're involved with. On the left is the magnetic susceptibility versus density for the ironstones, and you can see that there's a pretty good correlation here, as you'd expect. But the where the BIF's weathered, or you're in the magnetite breccia, you start to you actually density stays high, but you're starting to lose your magnetic susceptibility, certainly as you'd imagine through weathering. But I just wanted to show these quick 4 plots. So the top 2 are aeromagnetic surveys. So you can see that Osborne really stands out in the aeromagnetic data. It's one of the most intense anomalies, I think, in northwest Queensland, even let alone Queensland. And interestingly, these bottom 2 plots are gravity data. The one on the right is ground gravity, and that's the residual we've calculated there. And you can see that Osborne stands out on that data set. And then on the left is the Falcon gravity gradiometer data. And so you can see that the Osborne deposit stands out in that as well. So it's certainly a magnetic and a gravity anomaly. And now the last slide as well, if we stick with the geophysics, conductivity. So the discovery of Osborne, it was essentially a magnetic and an EM discovery undercover. And there's down on the bottom right here, you'll see a downhole log, and you can see it's essentially showing that these 2 ironstones, which not high-grade ironstones, 0.4 grams gold and 0.3 copper, and 0.5 gold and 0.5 copper, both their conductivity booms up to 5 to 10 ohm meters resistivity in the ironstones. So it is a conductive target. And I won't talk too much, but here's some airborne EM, and also this was the ground EM that was used to target the deposit down the bottom here. So, in summary, if we look at the mineralogy, silicification and replacement of feldspars and micas towards the mineralisation is an important process to keep in mind. Biotite, phlogopite potentially associated with the margins of the mineralisation. There's also anthophyllite, dolomite and talc present locally. The Aircore, end of hole geochemistry, is showing that there's a pretty fair size basement anomaly around the deposit in copper. I'm not sure about the other elements. and that various other elements are anomalous in the duricrusted surface and in the ferruginous layers in the Mesozoic cover. So that is sort of seeping up through the cover. There's strongly anomalous magnetic and lesser so gravity signature. And finally, that these ironstones, we can't say whether it's the mineralisation or the ironstones, are conductive and identified through 40 to 60 metres of Mesozoic cover. So, in summary, that's what the Osborne deposit looks like, and its immediate halo and signatures. So, thanks for that, Helen.
Thanks, Paul. Speedy summary. We've got one question, and we'll do that quickly before we move on. From 3 Sihalolo, what type of ore contains the rare earths in these deposit halos?
What type of ores contains the rare earths?
Rock types, I think.
What rock types? Well, I imagine it would be the alteration. It's essentially hosted in sammites and migmatites and granulites. So I suspect it would be the alteration, which we're now doing work on some of the, or starting work on some of the IOCG deposits in terms of rare earths up in northwest Queensland. It's, off the top of my head, I'm not quite sure which minerals are there that would be containing the rare earths, but I'd suspect maybe allanite may be in there. Somebody else may be able to provide any more information on that.
I think around the Mary Kathleen area, it's certainly allanite.
Yeah.
All right, we might leave it because we've got a lot to get through today.